Okay, Ruofan, please start.
Today, I will give a summary on model-dependent sample-based explanation methods for deep neural network. When we are talking about the explanation methods for deep neural network, there are basically two types of methods. First one is feature attribution. Basically, we want to understand what are the important features that contribute to the prediction. Some representative works are deep-lived, integrate gradients, deep sharp, grid cam, etc. And the second type is sample importance. That means we want to find the influential sample to the model. Some works are model agnostic. That means I only want to find prototypes or representative samples from the training data distribution without looking at the model.
I'm sorry, so what do you mean by the prototypes?
Prototypes just means representatives.
I see.
Or sometimes they are called proxies, this kind of, yeah.
Okay.
So in this presentation, we will look at the latter category, which is model dependent. And inside this model dependent, it can be further divided into two categories. First one is we look at influential training to the model. Second is we look at influential training to a particular testing data point.
So can I ask, so the mimic model based, do you have any example work?
Oh, it's like you use a random forest that to mimic the behavior of a deep neural network.
It's more like a mode abstraction, something like that. Okay.
And under the model-dependent sample-based explanation methods, based on the fundamental intuitions, the works can be divided into two branches. First branch is we would like to estimate how would the testing loss change if sample xj were removed from the training data. So there are several works like influence function, tracing. And the second branch is...
Sorry, so I just see the name of EIF. So do you remember when will the ICML outcome released?
It's in May. It's in May, middle of May.
In the middle of May, okay.
Yeah.
Yeah, good luck. Okay.
And as for the second branch, they are based on the representer point theorem, which is saying that any testing prediction can be expressed as a linear combination of training prediction. And under the first line of research, there is one work called tracing, which requires access to the intermediate checkpoints. So I call it in-processing methods because we need to look at the training process. The rest of methods are done on a well-trained model.
All right, so this is one kind of taxonomy, right? In processing, but basically our EIF is still need to process a little bit, right? To change the model. So if we're looking to whether we want to change the model to see the relation between the testing and training samples, EIF can be put together with the tracing.
Yes. Yes.
Yeah, I think that's different kind of taxonomy. Yeah, let's keep going on.
So let me give some notation definitions first. We denote X as the input space and dtrain as the training data. I use X prime to distinguish testing from training. And Y is the output space. F is the second last feature layer. Phi is the last feature layer before activation.
So phi is after approximation, softmax, right? So
before softmax.
Okay, sorry, phi is before softmax.
Before softmax.
Okay, I see. So can I say, is that argument saying correct? So an F function is a representation function, which learns a representation of each sample. And a phi is more like the result of the fitting or prediction. Okay.
Oh, and so phi is actually some parameters times f.
All right.
Yeah. And the prediction problem is trying to minimize the following empirical risk. The risk is the average of training loss.
All right.
So for the first type of solutions, we want to estimate the quantity. This is the testing loss defined on x prime. And theta hat minus j means xj were removed from the training data. And theta hat is the original trained parameters on the full training data set. So this will be the formula for theta hat and theta hat minus j. Theta hat is the original empirical risk. Theta hat minus j is we remove xj from the training loss.
All right.
And if we slightly modify the estimation goal to be the change in testing loss upon upweighting certain training point xj by epsilon, because removal is a special case of upweighting where epsilon takes value of -1/n. So we can replace the -1/n to be a random factor epsilon. And then my theta hat minus j epsilon will be a function in terms of epsilon.
I have no question here.
But we need to estimate this theta hat minus j because we don't want to retrain the model. And if we want to estimate the change in testing loss upon upweighting certain training point xj by epsilon, we can just take the derivative of testing loss with respect to epsilon. And here I omit the derivation. The basic idea is that my theta hat minus j epsilon is near theta hat. So I will do a second order Taylor expansion around theta hat for my testing loss and will get this quantity here.
So this is more as a formula from the ICML 17 paper, right? Okay. So any questions on these formulas? Just fine to raise any question. Especially you may raise a question like why it is a Hessian matrix, whatever. So I'm familiar with this part. So if anyone would like to raise questions, I think Ruofan will be good to explain it.
So I think the Hessian matrix comes from the second order term for this Taylor expansion, because the first order will be a gradient and second order will have a Hessian. And this Hessian is defined as the Hessian matrix, as the average of Hessian matrix over all training data.
Any question here? If no questions, let's move on. Kushit, do you have any question?
No.
Okay. That is fine, right? Okay.
Yeah, so let me give an interpretation for the three terms here. The first term you can see is the testing gradient with respect to model parameter. So it's the testing's dependence on the model. Second term is the Hessian matrix. It can model the training data's interaction with each other. Third term is training's influence on the model parameters. So we just times all the terms together.
So can you explain a bit in an intuitive way why the interaction between the training data matters for this inference function?
For example, you have some duplicate data inside your training. And if you remove one copy of the duplicate, that doesn't really affect your model, right? Since the other copy still exists in your model. So we need to model this kind of data's interaction.
Okay, so the example is about duplication, right?
Yeah.
So which means that if there's a duplications, which means that some second order gradients might be zero.
That means if you remove that data point, then this surface of this lost surface of parameters doesn't really change.
But the matrix change, right?
Change a little bit.
So the question is that how the interaction or how the relations between two samples affects the Hessian matrix, and how the Hessian matrix can further increase or decrease the inference function. Is there any causalities or causal explanation for that?
I don't have the causal explanation. The original paper didn't really provide such an exact explanation. They just give an intuition that the Hessian somehow can model the correlation between samples. I think the Hessian can somehow estimate the correlation between parameters, and the correlation between features is equivalent to the correlation between samples. Yeah.
And also the Hessian matrix is the Hessian matrix on every parameters, right?
That's the original definition. But in practice, I think we always take the last layer.
For efficiency consideration. We have a paper reviewed, and he claimed that how to select a specific layer of the parameters, it really matters. Okay.
So if we have an xj that have large absolute value of this influence value, then it is influential to the x prime. And the sign of IF can be interpreted. If the IF value is greater than 0, that means xj is harmful to x prime. Because if we upweight xj, we will observe that the testing loss will be increased. So that's why xj is harmful.
Keep going on.
There are some criticisms on the influence function. The first criticism is they did not explicitly model data's interaction. So this is raised by a work called Data Shipley. The second criticism is they think the top influential samples usually have high loss, which might be outliers or mislabeled data. And the third challenge is that computing this influence function is computationally expensive because of the Hessian inverse.
And for the second, so you have more detailed explanation for each item, right?
Yes.
Okay, can keep going. I can reframe my question.
So the original influence function tried to compare the changing testing loss when we train on the full training data versus full training data minus xj. But Deep Shipley is trying to compare the testing loss when we train on S plus xj versus S, where S can be any subset inside this D train minus xj. The basic idea of Shipley is Shipley tries to compute the real effect of a game player by averaging over all possible actions taken by other players. These players here, I think it means each training sample in our scenario. So this is the idea. This is like the idea of marginalization. We are trying to marginalize out the real effect of xj.
But the combinatorial complexity is quite high, right?
Yeah. So basically, we need to estimate this expectation over all possible S. But this theta hat trained on S plus xj will be far from the original theta hat. So we cannot use Taylor theorem to estimate this from the original theta hat. what they do is they need to fine-tune the model for one epoch of this x plus xj, and afterward estimate this quantity.
Which means that they need to fine-tune the model for a very large number of combinations.
Yes.
So any optimized approach to
they use multi-color estimate, so they don't exhaustively use all the
so
S.
they just sample
them.
the combinations in the combination space.
Yes.
I see.
I think it's theoretically grounded, but it's not necessary in practice to go over all the S. And it's more computationally expensive than IF. I don't agree that IF didn't consider data interaction. I think the Hessian inverse already captured that.
It is the data interaction in terms of the training loss, right? So maybe I have another questions for you. So for Hessian metrics, it actually calculate the interactions. If we just look into the metric per se, we just look into the interactions between two parameters, every pair of parameters.
Yes.
And how do you interpret or build the link between the interaction between the parameters into the interactions between the data?
Oh, for the details, you can look at the similarity of neural network revisited, that paper. That explains how you build the explanation, how you build the relationship from the interactions between parameters to interactions between samples. Yeah.
And do you have intuitive explanations, or we have to exhaustively go through the literatures to understand the relation?
I think it requires some mathematics derivation. Like you need to look at the metrics.
So which means that we haven't got intuitive explanation, at least for now. That's okay if we don't.
Show the.
That's okay if we don't have intuitions, and we can pause and maybe we can discuss this in the next meeting.
Oh, maybe I can show this formula. So basically, the left-hand side is the correlation between the samples, while the right-hand side is the correlation, is the similarity between features. So there's a formula.
I see the same formula before, but maybe I need you to help me recap a bit. So X times X transpose is the relation between the samples, right?
Oh, yes.
And Y times Y transforms is another kind of representations of the training samples.
Yeah, of the same set of training sample, but using another representation. And is equal to which is equal to the Frobenius norm of Y transpose X. And Y transpose X can be seen as the inner product between the features for Y and features for X. So
the question is that how can Y transpose times X, because the dimensionality between X, Y is not fixed, right? It could be any dimensionality.
Yes, but because they are computed on the same set of samples.
Yes, I understand. So for example, X have a very high dimension, have in very high dimensional space, Y in low dimensional space. So how Y, in this case, how Y transpose can times X?
Oh, because the second dimension of Y transpose should be the number of samples, and the first dimension of X should be the number of samples. So
I see.
The dimension aligns, but the feature dimension may not be the same, but you can compute. Yeah.
I see. Okay, so I have no question. Is there any questions here?
So what is VEC here mean? VEC.
Flatten it as a vector. Because this is a matrix, so you just flatten it as a vector.
Oh, okay, I see.
So I think the basic idea is that we're going to calculate the similarity between the representation of two just like neural net models, we learn different representations from different layers. Maybe this formula is going to calculate how the representations are close with each other, right? Okay, so maybe we can discuss this more offline. I assume that there's still a few slides. Okay, keep going on. Yeah.
And the second criticism is the top interstitial samples have high loss, which tend to be outliers. But I don't think this criticism is very strong.
I agree with you. So if that's the case, we can apply the inference function iteratively, right? So we can pick up the noise or mislabeled samples and and train the models and apply the inference function again. And then finally, we can find the one we are really interested in.
So one work called Relate IF tackles this problem by normalizing the original inference function with this quantity. Basically, they want to punish the training with really large gradients so that they will rank lower.
So the Relate IF means that is short for
relative. So they add a normalization term. But it's more computationally expensive because they need to estimate.
Sorry, so this is the solutions to address this outlier.
Yes.
So what if there's no outliers? Is that approach have a similar effect with IF?
Yes, it will have similar effect.
All right.
And I think outliers are indeed influential, so we should report them. Yeah. And the third criticism is it is computationally expensive. So there are two works working on this direction. One is tracing, second is our EIF. For the tracing, we need to make an assumption that we can trace the training process. Remember that the original IF estimates the change in testing loss caused by reweighting XJ, but tracing tries to estimate the change in testing loss caused by training XJ. So there's a slightly difference I want to emphasize.
I have no questions here.
So this is our goal. And if we just train on XJ and we observe the parameter update from theta t to theta t plus 1, then we can directly get this change in testing loss. Now we want to estimate the change by theta t only without looking at theta t plus 1. And we also assume that this theta t plus 1 is close to theta t. Then we can do a first order Taylor expansion for the testing loss from theta t. So this is the applying the Taylor expansion.
The first order, right? So
yeah. And we omit the second order and higher order terms. Then we move the testing loss for theta t to the left-hand side, and we get this estimation. But here we observe that the theta t plus 1 still exists on the right-hand side. So we need to express it in terms of theta t only. If we train on xj, we are doing gradient descent on xj. So the theta t plus 1 should be equal to theta t minus the learning rate times the gradient for xj. And we plug in to the original.
So very similar to the form. I still feel there's a similarity between the inference functions and this formula, right?
Yes, because for the inference function, they consider the second order, but here they only consider first order. That's
the argument is that there's no need to look into the second order, so we omitted the term of Hessian matrix, and it makes the formulas much intuitive.
But in practice, we usually
So actually, I think their name should be empirical, right?
So we usually train by mini batch, not sample by sample. So when we train by mini batch, then this theta t plus 1 should do gradient descent should do gradient descent based on the average gradient for every sample inside my batch T. So it's like this. And then the change in testing loss will be looking like this. And the contribution of xj to this change will be this. And the only difference is now we have a factor of 1 over the batch size.
Any questions? So on Xialing or Mengyue, do you have any questions for that?
No.
Okay, so it seems the presentation is clear. So maybe you can move on.
And the contribution of xj is cumulated throughout the whole training process. As long as this xj is included in the batch T, then we just add this quantity into the whole contribution of xj to x prime. And this T can be continuous iterations, or it can be checkpoints.
So maybe I raise a question. Yufan, are you still listening? Hello, Yufan. Maybe Yufan just hand on. Or maybe, no, maybe ask Changshan. Changshan, are you still listening? Okay.
Changshan just go to the bathroom, so he just.
Okay. So maybe I raise a question here. Ruofan just saying that this T can be either continuous or checkpoint, and I may ask why. So anyone would like to volunteer to answer the question? And what's the difference if the T is continuous and it's already will be a checkpoint, or which means it is discrete? Anyone would like to volunteer to answer this question?
T is the batch index, right?
Yeah, T is an epoch. I think it's the epoch number. Basically, I think it's not a batch index, it's an epoch number. So in that epoch, you can look into a set of batch. On maybe is T the batch index?
T is the epoch index or the iteration index.
But the BT
is the batch for at time T. It's the batch you look at time T.
Okay, so anyone would like to volunteer to answer the question? So what if T is continuous? What's the difference between when T is continuous or T is discrete? Or maybe Ruofan, you can answer the question.
Oh, when T is continuous, then the final estimate you get is more accurate. But when T is discrete,
it's just an estimation, right?
Yeah, but when we are training the model, we usually cannot save the model at every iteration. So we usually save checkpoints. So yeah, we can only achieve discrete estimate.
So when it continues, how do we do it? For example, it's like, let's say it is 10.5.
Oh, continuous means 1, 2, 3, 4, 5.
Yeah, okay.
Oh.
Cool. Understood. Thanks.
So in this case, what if T is equal to 1? How risky it is?
You mean you only have one checkpoint?
Yes.
So
I'm just linking. I'm linking this tracing.
Model.
I'm linking this tracing approach into our EIF, right? So basically, our approach is, we do claim that we can sample several epochs, but our experiments is just based on one sample, right?
Yeah.
More like T is equal to 1. The time the T is equal to 1.
But this time is is the final
is very
version
different,
of
right?
model.
You claim that the T is very different. Okay, maybe you can talk more offline to compare between the EIF and the tracing. Yeah, let's move on.
So the key assumption is that we need to have access to the intermediate checkpoints. So we are the owner of the model. And if we look at the formula, I think it basically tries to measure the agreement between the training gradient and the testing gradient. If they agree with each other, then xj will have large contribution to x prime.
Okay, that is intuitive. Okay, you're not talking about EIF, right? Okay, you can keep going on. Yeah.
Do I need to talk about EIF?
So you raise question here, or you just want to illustrate the idea here?
I just want to illustrate the idea.
But with some questions, right? Okay, keep going. You can keep going on. Yeah.
So in our EIF, we want to, because we basically want to estimate the change in testing loss caused by training xj, then we want to directly measure such a correlation between the change in testing loss and change in training loss. So our EIF is defined as the delta testing loss divided by delta training loss.
Okay, so I have no questions here. This is a formula.
So to estimate this quantity, we need to have a theta prime, where theta prime is the parameters after we training or reweighting or removing xj, etc. And we assume it follows a certain distribution p theta. If we know this p theta, then we can estimate this quantity by Monte Carlo estimate by drawing from this p theta. But we don't know this distribution p theta, so we empirically use some heuristic to sample this theta prime. We let the first theta prime to be the steepest gradient descent direction of the testing loss to get theta prime 1. And for theta prime 2, we let it to be the steepest ascent direction. And for the rest of theta, we let it to be orthogonal to the previous thetas. Then we can estimate this quantity. The reason we take the steepest descent or ascent direction because it can amplify the change in testing loss. So we think they are representative directions.
Okay, I have no questions here. So anyone have question for this illustration? Okay, maybe we can keep going on.
Let me illustrate the second type of research is they are based on the theorem called representer theorem. Let me introduce the theorem first. Consider any minimization problem of this form, where we try to minimize f. F is a prediction function. In our case, is our neural network. And we have some loss imposed on the training data from x1 to xn. We also have some regularization term on f. This regularization term is necessary for the representer theorem to hold, so it cannot be dropped. And the theorem is saying that if we minimize this optimization goal, we can get that the optimal solution can be expressed as the prediction at any point x can be expressed as a linear combination of the kernel between xi and x. Kernel is some similarity measure between the training data xi and the prediction and the testing data x.
Yeah, so this is so if you still remember when we attend the workshop in SMU, so Xiaofei was giving their ICML presentation. So basically but anyway, so their approach is to evaluate the inference functions on the RN, right? So the recurrent neural network models. So basically, they design a very complicated similarity measurements to estimate on the similarity between xi and x. So this is more like a kernel function, right? You can see they are inventing a kernel function which analyzing the internal signals representations, and but if there's if we're using the representative theory to explain it, they just have a special kernel function. But for alpha I, so they don't consider these. But if they can calculate the alpha layers, maybe they have they're more optimized. Might be, I'm just saying might be. They have a more optimized alpha to further improve their effectiveness.
Yes. And this alpha I times kernel can be used as the contribution of xi to x.
Oh, by the way, though, you have a slice here, which means that the Jonathan's actually giving these kind of explanations or in their courses, right?
Yes, it is in this course.
And Xiangling also attend the course?
Yes.
Okay, so Xiangling is also understand this represent theory.
I think this theorem also Jingyan also explained this, right?
Yes, that's last presentation. Yeah. So you're, I mean, before that presentations, in your course, you also learned the theorem.
I guess I don't remember.
All right. Okay, let's keep going.
So for the RPS L2 published in NeurIPS 18, they just use L2 regularization on the last layer's weight. And they derive that this alpha I will take this form. And the kernel function is simply the inner product similarity between the train and test in terms of the feature layer. The alpha I can be interpreted as the training's influence on the model parameters, because again, we see this gradient of training loss. The criticism on this work is the influence is dominated by alpha I, not the similarity term. So they find that the explanations tend to be identical for different testing samples within the falling into the same class.
And so in these formulas, maybe I raise a question. You find, are you still listening? Maybe I raise the questions to Xiangling. So can you explain, Xiangling is still there, right? So maybe I ask questions to you. So Ruofan is claiming that the inference is dominated by the alpha I, which makes all the explanations to be identical to different testing sets. So can you explain why that is the case?
I think similar testing, the representation of
do you have any questions? Because in these presentations, you are so quiet, so much silence. So I just try to make sure that you really understand those ideas.
Yeah, personally, I think because the representation of all the samples from the same class is very similar. So
sorry, yeah, the representation of what?
Of all the samples from the same class are very similar.
Are very similar.
So fx prime should be quite similar for all x prime from the same class. So they would just provide.
Sorry, Ruofan. So is that an xj to x prime or xi to x prime?
Xi to x.
Right. So it's right. Okay. So
because the green term are fixed, and fxi also fixed because it's from training data set. So here the only difference is fx prime, and I think all the representation should be similar from the same class. So they provide the same explanation. Yeah. That's why I understand.
So in that case, if I understand correctly, Xiangling have a different interpretations than from Ruofan to explain why the explanation are identical, right? Ruofan, have you listened to Xiangling's explanation?
Yes.
It is her explanation is different from yours, right?
Yeah.
What did
So the case is that, so I just explained the spoiler phenomenon here. So Ruofan provided explanations to get a conclusion. So I raise the questions to Xiangling. So why the conclusion is here? And the idea is that I want to confirm whether Xiangling agree or understand Ruofan's explanation. But the solution turns out that based on the conclusions, Xiangling develop another completely different interpretations than Ruofan's to showing that he understands Ruofan. Okay.
I agree with Ruofan for the second point, but I just remember that the experiment result from the RPS L2 norm that they provide some identical explanations for.
Yeah. So you agree with the conclusion, which means that you agree with the conclusion because you pay attention to the presentation last time. Yeah.
No. I mean there might be some variation. I mean there might be some outlier, but
this is the NeurIPS 18, right? This is NeurIPS 18. It's not the improved version.
Not the improved. Oh, I think this is actually explained by Jing Lian last time. So.
Yeah, actually, we don't know the answer. We just take the conclusions or explanations from all the literature. We haven't evaluated by ourselves, right?
So the idea is that the green part will be larger than the orange part. And this green part does not involve in X prime, which is the testing data. And if we change the X prime.
And also XI is also the training data, right?
Oh yeah, XI is also the training data. If we change X prime.
Oh, sorry, the X prime is the training, the testing data.
The testing data. If we change X prime, this term will be changed. But because the alpha I is too large, so the change in the similarity is not very obvious if we look at the influence value.
So they empirically evaluate the value of each items and have the conclusion.
Yeah.
But I still want to say that if we don't have the conclusion or the empirical results, Xiangling's explanations might also work, right? You can think about it. So the idea is that suppose the explanations come from the class instead of individual samples. In the meantime, the representations of each samples, because Xiangling works on the visualization, they see that after trainings, all the representations are clustered together, has very high cohesions. So in this case, we're saying that suppose they have several for each HXI, if their representation is very, very similar, so they will provide a similar kind of a inference function that also work. Yeah, that didn't work. But for Ruofan,
or based on they have a scatter plot to prove this criticism. So
the statement has been kind of justified based on the experiment, right? Okay.
Yes.
Okay. So. So Changshen is Changshen still in the toilet? Anyway, so I don't raise any question here. So maybe Ruofan can move on.
And the second point is that because RPS relies on regularization term, so this is needed in order to apply the theorem. So in RPS LGE, which is presented last week, they no longer need the L2 regularization. And their derivation is based on, again, the first order Taylor expansion. And after the Taylor expansion, they find that the new alpha F will take this form. The kernel function is the same.
Alpha is different.
Alpha is different.
Yeah, I forgot about how they induce the presentation. But never mind. If you have any questions, maybe refer to Jing Lian's presentations last week.
And it turns out that surprisingly, RPS LJE has subtle difference to the original influence function. I highlight the common terms in orange. And the reason is that both are based on Taylor expansion around theta hat. So I think it makes marginal contribution from the influence function.
No, it did not make marginal inference function. They using totally different approach.
No. It should not be called RPS because the derivation no longer depends on RPS theorem. The derivation only based on the Taylor expansion. So it's actually the same as influence function.
So the idea is that they remove the regularization term, right?
Yes.
But they still want to have this form.
It's like another way of interpret influence function. Because you can also interpret the original.
The Taylor expansion is a tool used either in RPS LJE and inference function.
Yes.
But they are expanded in a different way, right? So RPS LJE is based on RPS, and RPS is based on the representation theory.
RPS LJE is not based on RPS because it did not use RPS anymore.
Oh, maybe I forgot the presentations. Maybe you can discuss this more offline.
Yeah. So it removed the L2 regularization. It removed the RPS theory.
But when
it's
it
totally
removed,
based on
I got a point. If it totally removed the, if it totally based on the Taylor expansions and how they have the F transpose times F, how they derive this term? Inference function don't have these F transpose times F, right?
You can apply chain rule to get this F because F is, remember, is the second last feature layer. So we can apply the chain rule. We plug in the F, and so we can get the expression for F.
All right, see.
So this is done by the RPS LJE paper, and this.
So your claim is that RPS LJE is just a trick applied on inference function, so that we can get a form of F transpose times F. So basically, it is just a trick on the formula manipulations, and they got into another NeurIPS paper. So that's what they claim. Right?
Yes, because this statement is coming from their paper. So they mentioned that they have subtle difference to IF.
Okay, I see. I see. Yeah, if on the reviewers, they will be tricked.
And it still
may I ask how about besides this formulation and their results also very similar to IF, right?
Yes.
Okay.
The qualitative results also shows the similarity.
Okay.
And it did not solve the computation complexity problem.
Yeah, so I think here, one is, okay, you're looking into the Xiaofei's work now. Okay. Yeah, I have comments here on the last slide. So we have a paper I will review it, and this paper is very likely to be accepted in the ICML this year. The idea is that they're going to have, they're looking to a very special case where the NLP is applied. They're going to say on which testing sample, which training samples will contribute to the final prediction, and their analysis about a sentimental analysis. So given a sentence, we'll say whether it is positive or negative comments. And since now the NLP models is largely based on the BERT models, transformers, which means that if we look into the Hessing matrix, it will be huge, right? So their contribution lies in, they claim that they're the specific layers in a transformer, which has the best effectiveness, which has the best, which is best to serve as a term in the inference function. And they also have some way to optimize and reduce the matrix, the dimensionality of the matrix, so that they claim that they have a more efficient way to calculate the inference function.
Oh.
Yeah, and I think they're might interesting to look into more on. You can say there are so many parameters and some important, and some more important than the others. Maybe that is also a direction to see, but it's a very pure. It's almost pure AI. It's different from the other area like software engineering. Okay, let's keep going on.
And this is the work presented in last week's workshop. Basically, they define a customized kernel to measure the similarity between two sequences, right? Two sequences. But they did not consider the alpha I.
All right. Okay.
So this is the taxonomy. And because of RPS LJE, it built a link from this branch to the inference function branch. The comparison, I have a comparison on the complexity. I think the costly methods are data shapely and relate IF. The more practical methods are listed here.
Okay, so yeah, that based on Ruofan explanations and these taxonomies, it's very reasonable. So I think the IF is, I think that is the best paper on in ICML 17, right? Yeah, that is best paper, and following this work, a lot of work on trying to improve the efficiency. All right. I don't have any questions here. Okay, Ruofan provided the slides for discussion, right?
Basically, there are two ways to measure training influences on testing. First is we directly estimate the change in testing loss. The basic idea is we get the training influence on the model, then times the model's influence on testing. Second way is we measure the similarity between training and testing. So we get the training influence on the model, then times the similarity between train and test.
And so what is discussion? I assume that you will raise some questions to involve the discussion, and I think you just throw away some clues and what is the link or question for us to discuss.
It's like a summary.
All right. Okay.
Sorry, about the second one, similarity between train and test. Is training data or testing all the features?
Yes, there's a lot of way to define similarity between training sample and testing samples. But if we really want to apply it, we still need to have some formula derivations to have that. But anyway, we can see even if we don't consider the alpha, and the Xiaofei still managed to publish ICML, right? As long as similarity measurement is interesting. Okay, let's keep going on.
As for the evaluation method, the original way of evaluating is we do mislabeled data identification by self-influence using the polluted labels. The assumption is that mislabeled data have high loss since their labels are incorrect, so they will be influential. However, the mislabeled data that are predicted as polluted are no longer influential, so the mislabeled data does not necessarily mean influential. And this kind of evaluation method might be problematic.
Yeah, I think one of the arguments you can refer to Xiaofei's presentation, right? So they just pick up the polluted samples which have the correct prediction. So they say those part of the polluted samples are really inferential. And for another kind of samples, they may or may not be inferential. Right. So and after all, we need a ground. We need a ground truth to know that which samples are really inferential.
So these are the formulas for self-influence. Basically, we replace the x prime as xj. And for RPS-based methods, the kernel will disappear because it's measuring the similarity to itself. And for tracing, we are basically measuring the norm. The second way of evaluation is we do misable data allocation by influence on the testing error. So we do not use self-influence. RNA repair use this evaluation method.
Mislabel. All right. That two works are just invented by two software engineering people. Think alike, yeah.
And the third way of evaluation is our evaluation method. We basically literally upweight and downweight those helpful and harmful training samples identified. Then we fine-tune the model and track the real change in the testing loss.
Okay.
That's all for my presentation.
Yeah, I think that's a very great presentation. And I don't have more questions, but I think from people work on different questions. I think inference function might be a tool for us to be aware to use. For example, if one day we want to understand whether a model have a problems, inference function is a definite tool. And there's a lot of tools there have a lot of tools invented here. And maybe in the future, there's more flexible, maybe there's a library for us to use. But anyway, the tool is there, and it's good for us to know that we can use that kind of tool to explain and understand our model. All right, I don't
sorry,
have...
can I ask a question? How
Okay.
you upweight and downweight? I mean the samples.
From our experiment, we just zero out the weight for harmful and double the weight for helpful.
I see.
And then return the model.
Zero out, that means remove. Double.
Double means add an example, and zero means we removed it, totally removed it.
Double means, sorry, double means
add one more samples, like.
Okay, I see. Thank you.
I also wanted to ask one thing. So imagine some complex architectures, for example, again, object detection, let's say. We may train our backbone in a different data set, let's say ImageNet, and use it for a downstream task for object detection, right? So ImageNet is classification, and then we do some pre-training or linear probing kind of thing. Right, so the training itself contains several phases. How should we proceed if you want to measure the influence of the training data in the pre-training phase? So we want to measure the influence of a classification data sample into an object detection data sample, let's say.
Yeah, maybe Ruofan can try to explain the questions. So the idea, so maybe I rephrase on Kushit's question is that if for more complicated training procedures like object detectors, you have more like regressions, classifications, right? So if the regression problem means that we need to know the borders, the boxes, where the box is. So in that case, how do we, and there's several stages, and how do we evaluate the inference of the training sample, like classifications, to the final object detectors or object detection result?
I think you can measure the influence in different stage and then times them together.
Using the chain rule, right?
Yeah.
So it's just a math trick.
Yeah, I think that's a very interesting question to ask. Maybe we can work on that. So how, so there's the first stage, right? If for a fast RCN, right, you're talking about a fast RCN, supposedly that is structure or friend detections. We want to see there are several stages of training and how the samples influence on how the samples in previous stage can influence the last stage. Or maybe you can ask another question is whether this cross-stage influence helps, whether it helps a lot or whether it can can be for us to have some repair solution.
Yeah, I was just asking because I read a paper recently which compared the effectiveness of fine tuning and linear solving. So and just wondering. Thanks.
Okay, so any other question? Just feel free to ask. If there's no questions, maybe we'll call it a day. And thanks, Ruofan, for the great preparation. Okay, bye.
One moment.
Okay.
So next week, I guess I